Hey YouTube, and welcome to the last of the videos here for logarithmic functions. Last video, I suppose, for the term. Now, we have been integrating differentiating functions with logs of base e, and sometimes exponentials of base e, and a base of e and calculus work together beautifully. If I have a different base, what I'm going to have to do is change that to a base of e so that it works more smoothly. So first of all, we are going to differentiate these functions here. They don't have a base of e, so I'm going to change them. Right? Now, we might remember that our change of base tells us that the log base 2 of x is the same as, let's say, log base e of x over the log base e of 2. And I'm going to rewrite that a little bit as 1 over the log base e of 2 times log base e of x, just so I can see this here is a constant, right? Constant times this. So if I differentiate that, I get, right, let's do this part first. Differentiate this, I get 1 over x, and that's just a constant. So I get 1 over x log base e of 2. That's all. Now, the same thing's going to happen here. We'll go through the same process. So, therefore, y equals, I'm going to say this is the log base e of x times, I'm going to say 1 over, right? Instead of divided by, it just makes it a little easier here, over the log base e of a. Therefore, y prime equals different 1 over x times this log base e of a. We can sort of rely on this now as a general form, I suppose. Right, if I'm differentiating a logarithm of a base other than e, we can look at it as this. 1 over x log of the base to a base of e. Right, check that out. Now, differentiating and integrating exponential functions with other bases. Now, really, I would suggest that this identity here is pretty useful. A to the x equals, oh, there's a little bit missing here. That's e to the log a to the x. That a to the x we could write as e to the power of x log a. Right, I think that identity there is going to help us out a lot here. So we want to differentiate this. That's a little difficult, but I'm going to say y equals, instead of 2 to the x, I'm going to say that is e to the x log 2. Therefore, y prime equals, right, remember when I differentiate an exponential function, I differentiate the top, bring that down, differential of this is the log of 2, and I repeat this, e to the x log 2. Now remembering that e to the x log 2 is the same as 2 to the x, right, that's that identity. E to the x log 2, 2 to the x. I could write that, but I'm happy enough with this. And we want to find the gradient of this line at the y-intercept. The y-intercept is when x equals 0. X equals 0, therefore my derivative, right, which is my gradient, equals the log of 2 times e to the 0 equals the log of 2. Now it says to 3 significant figures, right, my handy calculator, here it is, and I can do the log, what are you hiding here? I haven't been using this a lot lately. The log of 2 equals 0.6931. Is that right? 3 significant figures equals 0.69, was it 3? 0.693. Okay. Right, there's that first one done. All good. Another one here. Show that these lines meet at this point here. Look, I'll work through this quickly. Oh, don't do that to me. Not that one. Here we go. Sorry. Now, y equals x plus 1. Let's look at this one here. And y equals 2 to the x. Sub 0, 1 into both of them. So I get my left-hand side. I really don't like substituting directly in and saying, oh, look, it's equal, it's not equal. We should really do this. Left-hand side equals 1. Right-hand side equals 0 plus 1 equals 1 equals the left-hand side. So that's good there. Left-hand side equals 1. Right-hand side equals 2 to the 0 equals 1 equals the left-hand side. Okay, so the 0.01 is good. Let's check the other one. The 0.12. Left-hand side equals 2. The right-hand side equals 1 plus 1 equals 2. That's tough maths going on there, isn't it? Equals the left-hand side. Okay, so the 0.12 works for this one. Does it work over here? 2. The left-hand side equals 2. The right-hand side equals 2 to the 1 equals 2 equals the left-hand side. So that's part A done. It's pretty painful. We can't really do it another way. Sketch the two curves and shade the region contained between them. Right, x plus 1 and 2 to the x. Fortunately, this is my last page. I'm going to need a bit of space here. Now, I'm actually going to do... Let's do this. Now, this crosses here at 1. And a rule is going to help here, and I don't know if I've got a tool that might help me out. Boo, that did not work. Right, a ruler would be really helpful, but you have to draw, right? I'm not going to start this again. You have to draw these things pretty accurately. Right, you will lose marks if you are sketching things and you haven't drawn it sufficiently clearly. This is looking a little bit better. Right, there's my x-axis, my y-axis. This is 2 to the x, and this is, what was it? Y equals x plus 1. Righto, the region in between is this region in here. It's only a little sliver of a region. I'm not expecting a giant answer. Okay, so that's what I'm after. We know that there is at x equals 1. So, I need to find my area is equal to the integral from 0 to 1 of x plus 1 minus 2 to the x dx. Keep in mind, I can't integrate 2 to the x, but I can integrate from 0 to 1 of x plus 1. Now, minus, come back to our identity here. Remember that 2 to the x we could say is e to the x log base e of 2 dx, and I can integrate that. So, this equals the integral of x, half x squared. The integral of 1 is x. Now, if I've got to integrate this, what I would need to do is have negative 1 over log base e of 2 times e to the x log base e of 2. Looks pretty heavy duty, but it'll be alright. From 0 to 1. Okay. Now, we need to substitute in here, and then we're going to get it out in our calculator, but I'll do the substitution first. Put 1 in there, what do I get? Half of 1 squared, half. What's going on here? Plus, there's a plus sign in there. 1 in there, that's fine. Plus 1. Now, into this expression here, that I'm afraid I may not have written neatly enough, but we're going to replace our x with a 1. Everything else is constant here. So, I have e to the log base e of 2. Now remember, e to the log of something is just that thing there. So this is minus 2 over log base e of 2. Go back and check that if you like. Let's see that for this term here, when x equals 1, all of this equals 2, right? That's one of our log laws. So we get this, minus, now I've got to substitute the 0 in. Now this is fine, I get a 0, plus a 0. Now I put a 0 in here, I get e to the 0 of something. So I get 1 over, so minus 1 over log base e of 2. Be careful of the double negative here, that's an easy way to get this wrong, is 1.5. Now that becomes a plus, so I get minus 1 over log base e of 2. Now it does ask for this to four significant figures, so grab out our trusty calculator again. I'm getting a 1.5 minus, so 1 over log of 2, closing bracket I suppose, equals, check that looks right. You can see here the new calculator, right, that's fairly nice to see what's going on there, equals 0.05, check our use of significant figures, 5730. 730 square units for significant figures. And there we go. That's the last of the problems here for logarithmic functions. Hope you enjoyed as much as I did. I loved it. Okay, see you in class.